This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
For Software Engineering Radio, this is Robert. I'm joined today by Josiah Carlson. Dr. Carlson has his PhD in computer science from the University of California, Irvine. He's been a software engineer and architect at several technology companies, among them Google and YouTube, with a focus on architecture, design, algorithms, and distributed systems. He is the founder and chief architect of ChowNow and is currently an advisor. He is now the chief architect at Zeconomy. He is also the author of the book Redis in Action. Welcome to Software Engineering Radio, Josiah.
Thank you. It's good to be here.
Today, Josiah and I will be discussing Redis. Let's start out with, what is Redis?
Well, Redis is an in-memory key data structure server. It is most commonly compared to a system called Memcached, which stores string keys to string values, and where Redis majorly differs is that it maps from string keys to data structures. You can have one of several types of structures, among which being plain strings, lists, sets, hashes, and what are called sorted sets. There recently has been an addition that offers a type of aggregate for counting unique things statistically, called a HyperLog Log that was added, but that's fairly new, like literally in the last couple weeks, so not that many people have used it yet.
You said Redis is a key data structure server. How does that differ from a key value store?
The primary difference is the types of things that you can do to your data. In a typical key string server, called a MAC, you can basically get or set values. Sometimes the values can be incremented, like, say, an integer or a floating point number. And sometimes you can even append data to your string, so you can keep making your string longer. With Redis, you can do all those things too, but with the additional structures, say lists, you can also push and pop from both ends of the list. You can look for items in the list. With sets, you basically get a unique mathematical set concept. So if you want to, so say you add the string hello twice, there will only be one in it. For hashes, it is a typical hash that maps from keys to values again, and it has all the typical set interactions, hash interactions that you would expect. And sorted sets are a little bit funky in that they behave a lot like a hash, where you can also access your items by the sorted order of what would be the equivalent of a value, which are called scores. And so it offers different access characteristics, and each one of them offers different read, write, and access characteristics.
So Josiah, you're talking about the ability to modify these data structures server-side. What's the thinking behind server-side data structures rather than client manipulating data structures and pushing them back as an opaque value?
So primarily it has to do with the amount of data you need to transfer. Say, for example, you were using strictly Memcached, and you could send and receive strings. Now, certainly you can store, more or less arbitrary data structures with JSON or message pack, and a lot of people do that. But then anytime you want to change the structure, you first have to read the whole structure, modify it, and write it back. And then in that process, you have to somehow lock that data so that somebody else doesn't read it modify it, and then write it. And while you can certainly do that, directly manipulating the objects themselves is a lot more efficient in terms of CPU time because you're not encoding and decoding. It's a lot more efficient in terms of network bandwidth because you're not reading and writing the full value. You're just modifying small pieces.
That makes a lot of sense. In your book, you work out a number of interesting examples of how Redis can do some very powerful things. Could you walk us through a small example that shows how you might use one or two data structures to develop an interesting feature?
Certainly. So one of my preferred patterns in how I deal with storing and sorting data is one that's already built into Redis. It's pretty common, and that is the use of a set and the use of a collection of hashes. Now, generally speaking, a lot of people will use a hash as sort of like the equivalent of a document in a document store or even a row in a relational database, where each field in the hash is the equivalent of a column or an attribute. And people store their data like this, and this is great. You know, you can fetch the whole thing, you can fetch individual fields, but what you really get when you really start thinking about what you can do, you can then start sorting data that you have. If you were to put an identifier for each of your hashes, say for example your hashes are named user : and then an ID number as the key, and then you have a set with each of those IDs in it, and say it was stored as users : and that's the key name, then what you could do is you can get a sorted order of any arbitrary column equivalent on your hashes. You would say sort this set by, and then you can actually provide a string, and that string could be depending on the column. Say you want to sort by email address, and you've got email in there. You could say user : star, which is a wildcard, and then you could draw, and you can type it a hyphen and then the greater than sign to create a small arrow. And then for the field, you would type email. And if you say sort that set by, and you provide that string, that tells Redis to sort that set by fields referenced in other hashes. And if you also provide the final word of alpha to tell it to sort alphanumerically, you then get a sorted, then the items that are returned by that sort call are ordered by the email. And this is all built into Redis already, and these are known patterns, but it's still really useful if you to offer effectively arbitrary sorts on your data, even when you've not set up an index, you've not set up anything special, but you still get the ability to perform ad hoc sort queries, which is very powerful, and it's something that not everybody would necessarily expect.
You bring up another point in that example. Does Redis offer a wildcard expansion on a key substring?
It depends on the context. Right now, the only situation where you get it strictly in this kind of thing is with the sort command. Now there are other commands, like Redis also supports a pattern known as publish subscribe, where you can publish to channels and you can subscribe to channels to receive messages. There is a pattern subscribe call which lets you subscribe to arbitrary patterns, and you can provide the wildcard character *, which will then match anything. And you can also use that if you're looking to find keys using the keys command, or using the, I believe it is S keys, or something similar, new command to actually traverse the known scan. Also takes wildcards, but that's not so much expansion as much as it is a wildcard.
You mentioned a new feature, the HyperLog Log, which I'm not familiar with. Tell us what problem that solves and how it works.
Certainly. So one fairly typical usage of Redis is for, say, for example, unique visitor counts at web pages. One way of doing that, not necessarily the best way, but one way of doing that is when you assign a cookie to your visitors to uniquely identify them, whenever they visit, you then, say for example, add them to a set, because sets only contain unique items. When you add their user ID to the set, they're only in there once. So if you say create a set and use it for 1 week, then you get unique visitors for that week. This works great. Of course, the problem is that you need to use a bit of memory for every person that visits. And so for large websites, that would require a lot of space. Now there are a bunch of different ways that you can change it and improve it and reduce the amount of memory that you use. And HyperLog Log was recently added to offer this. Now it's not just for counting website visitors. But what it can do is, when you add items to your HyperLog Log, it doesn't add them, it statistically adds them. It computes a hash on the item that you're adding and flips some bits in a small structure, and then it uses how many bits have been flipped to determine an estimate on the number of unique items. Salvatore spent a bunch of time analyzing it and figuring out how we can optimize and somewhat minimize the error. And I think right now for the large sets, that is for large groups of items that you'd like to count, it is within 1 or 2% of the true actual value if you were to calculate it by adding to a giant set. But it only takes up, I believe, around 12 kilobytes. So for 12 kilobytes, you can count to really, really, really big numbers.
It sounds something like a Bloom filter, if I understand it correctly.
Yes, it's similar to a Bloom filter. The difference primarily being that a Bloom filter is meant to be significantly larger and store yes or no, this item is in it, or no, this item is not in it, and that's not really what what HyperLog Log is supposed to do. But a lot of the same ideas go into making them both work.
In some of these examples you're giving, they involve multiple data structures, which naturally leads to questions about a consistency model and atomic operations. What kind of models does Redis provide for those considerations?
Individual commands in Redis are themselves atomic. If you push an item onto a list, another process pushing an item onto the list is not going to replace the item that you just pushed because they happen at the same time. Redis is single-threaded, so each operation individually is atomic because only one thing can happen at one time. For multi-command consistency, you can set up what are called transactions. Now, there are two basic types of transactions. One is just a strict, we generally call a multi-exec transaction, where you say, do these things all together when exec is called. And so you say multi, you put all of your manipulation commands in, and then you say exec, and when exec hits, all of those commands are executed one right after another without any interruption by other connections or commands. You can also perform conditional transactions using watch. So the typical thing is you say, I want to watch these keys for changes, and then you get data from them if necessary, and then you type multi, and then you perform your set of operations, and then you send your set of operations, and then when you say exec, what happens is before the multi-exec portion is executed, any of the keys that you said that you wanted to watch at the beginning, if any of them have changed, then the multi-exec transaction is actually aborted. You get an error message saying, hey, these keys have changed. And then if you'd like, you can retry. If there were no changes, then it will execute and you will get the response that you were expecting. At least no errors anyways. And then Lua scripting itself lets you do somewhat arbitrarily complex data manipulations, and the Lua script itself is considered more or less one command, and so is also executed atomically. There are some caveats when it comes to if you're in a Lua script and you're accessing a key that has just been expired, but it's not all that surprising.
With Redis being single-threaded, if you send a batch of commands and it executes them all on the server, there's not really any issue of whether it's atomic or consistent. It will all happen at once. This optimistic locking model, it must be designed to deal with environments where the client is going back and forth a few times before committing.
Yes, so it is indeed the case that the conditional execution or this optimistic execution does require a few round trips. I believe that it was originally designed like that because it's a lot easier to make what are called deadlock-free algorithms when you don't, explicitly lock data from modification. One thing that happens periodically in relational databases, if you are not careful, is that you have, say for example, you have two clients. One client locks row A and then tries to lock row B, but second client has already locked row B and tries to lock row A and then can't. And so they're in a deadlock situation because they want to lock data that the other one has already locked. That's very dangerous. But with the optimistic locking, or with the watch these things, if they change, stop it, otherwise let it go, you don't have any deadlock scenarios. You just keep retrying until your data modifications get through. And so from a execution standpoint, it allows Redis to be far more simple, even if it takes a little bit more work on the client.
Josiah, in your book, you give some examples of building application-level locks. What is your thought process on when you'd use an application-level lock and when you'd use the native locking that's supported by the server?
Generally speaking, I look at how complex are my data interactions. For Redis-style transactions, I will typically use them when the type of data being accessed is simple and my accesses are simple, and when I only need to manipulate maybe one or two structures in Redis. If the manipulations are simple, then, and the number of structures that I'm manipulating are one or two, then I can expect that the number of retries will be low. And if the number of retries are low, then I can feel pretty good that it will execute fast and efficiently, and I won't have any issues. When I need to manipulate things in Redis where there are perhaps many structures that I'm manipulating, or where I need to fetch data externally after locking data in Redis, then I will use an application level lock that is provided in the book. I use this because when your data manipulations include things exterior to Redis, then Redis is not going to be able to watch them, obviously. And when you are manipulating many things, you increase the likelihood that your optimistic locking is not going to succeed, and so you'll have to retry. And in various situations, some of which I bring up in the book, like the marketplace, using a lock is substantially faster. And so sometimes I look at it in terms of performance as well. That said, locking itself, if you use a Lua script, many times you don't even need to lock. And if you can embed all of your data manipulation in a single Lua script, then you don't need to lock, you don't need to use conditional locking, you don't need to use optimistic locking, you don't need to use Redis transactions. You just use a Lua script and almost always get what you're looking for. And incidentally, because those are typically just one round trip, you also end up performing faster as well.
You mentioned the Lua scripting a couple of times. I'm aware that Redis natively supports Lua on the server side. Tell us more about the language Lua first, and then I'd like to come back to what you can do with it that goes beyond the basic Redis commands.
My exposure to Lua is primarily through Redis. Years ago, when I was playing World of Warcraft, I got a little bit of Lua experience there. But Lua itself is primarily an interpreted programming language. It's fairly dynamic, but also fairly simple. It is designed to be small, and so it is very often used as an embedded programming language in video games, in applications, and in this case, in Redis itself as the scripting language. The variant of Lua that is included in Redis is Lua 5.1, which can be replaced with LuaJIT, which is a just-in-time compiler for Lua, but it is not included with Redis by default because the interpretation leads to more consistent performance, even though LuaJIT can execute faster in some cases. While I personally have been a huge Python guy for many years, and though Lua is a little bit is missing some of the features that I'm used to, so far I've personally not had any problems using it. And so far I've actually advocated for the converting of as many commands into Lua-based commands as possible, just to allow for better understanding and better remixing from others. But so far nobody's bitten on that.
And is the primary use case of Lua so that you can do a series of operations on the server without as many round trips, and therefore reduce the number of round trips, but also the locking?
I'm not sure whether it's strictly for that. I think it's just for the sake of flexibility. Many relational databases will have internal scripting languages. PL SQL being one of the more common. You take Postgres, and it's got more than a dozen internal programming languages that you can use: Python, Perl, PHP, Lua, Java, and various others. And so the concept is not so much new. Other databases have embedded programming languages in them. What this brings to Redis is primarily just flexibility. If you want, you can use it to do huge data updates in a single round trip. You can embed some level of your program logic. A couple years ago at RedisConf, this would be a year and a half ago now, there's a group called And Yet that had actually built their data validation and schema validation for Redis as effectively their full-time data store. They did all of their data type verification and constraint verification inside Redis using Lua scripting, which is kind of mind-boggling. But they did it because Redis doesn't support data verification by default, and they didn't want to write it on the client. So I thought that was very interesting and very innovative to use Redis to verify its own data internally when it normally doesn't, at least not to the extent that they needed to.
I want to switch over a bit, talking more about the memory and persistence issue. I think of Redis primarily as an in-memory data store with some persistence capabilities that we'll get to. Is that a fair characterization?
I wouldn't call it unfair. It is certainly the case that by default, the Redis that is shipped is everything in memory. Older versions had what was called a virtual memory interface, where it would swap unused data out, but that wasn't very efficient and got no love for many years, so was removed in Redis 2.4.
Okay. Now, as an application architect, Josiah, how do you think about the role of an in-memory server in your entire system compared to where you would use a database, meaning something that has a durability property on commits?
So I typically, personally, when I give people advice, will tell people to at least start with data that is perhaps less important to keep 100%. Say, for example, if you're running a web service, one of the first things that I recommend that people use is to use Redis to store their user session cookies. Typically, in web properties, you use a cookie to store user identification information along with many other things. But every time a web request comes in, including for your static assets and anything else like that, you have to send the cookie. If you have enough data in your cookies, that can actually be measurable, especially on mobile. But if you have, say, a randomly generated cookie identifier that then maps into Redis, where you store arbitrary user data, then you can minimize the amount of data transferred by your clients while also storing arbitrarily rich information about them inside Redis. Then your only concern if, what if Redis dies on me? What if I lose all of my information? What if I'm not backing up my data? What if I'm not replicating my data? What if I'm not keeping copies of my data somewhere else just in case? Well, you've just lost your login cookie. Start up a new Redis and then people have got to log in again. Not that big of a deal. And I find that that's usually a good introduction to Redis for a lot of people that want to use it. And then from there, after you see how fast it is, how well it works, once you get used to it, then you notice, well, wait a second, Redis hasn't crashed on me. The only issues I've ever had with Redis has not been with Redis, it's been with the server that Redis runs on. If you're in a cloud provider, sometimes those problems occur more often. But typically that's the way it is. Redis is a pretty reliable piece of software, and it is constantly being updated and fixed. And it's been very, very reliable for me. I've been using it for a little over 4 years now, and I think I've only run into 2 or 3 situations in those 4 years where Redis has ever had an issue where I've had a problem.
You talked about using Redis in situations where the data is not absolutely essential to preserve every piece of it. Maybe if you lost a little data, it wouldn't be a disaster. Because you're giving up the durability property, from an architecture standpoint, it has to give you back something in exchange for giving up durability. And what is that?
Primarily what Redis gives you for reducing your durability is a data model that is not currently replicated in any other database. The rich data structures that are available in Redis lets you model your application like you do in your typical programming language. What do you use in your typical programming language to model data? Well, you've got lists, you've got hashes, and you've got strings. Okay, those are the typical things. Now, Sets are less common, but they exist in some programming languages, like Python. And sorted sets are not generally available in most programming languages, but you can use them to build sorted indexes. So that's what most people do. But given these structures, you can structure your data in Redis like you would in your application. And then what you can do is you can just use Redis as your giant shared memory pool. Instead of having all of your user object that you're manipulating, say you're incrementing their visit count, or you are keeping a history of the recent pages they've visited. Instead of inserting a row in a database, you can just push an item to the end of a list. And if you want to cap that number of items at, say, 50, you can then trim the list. Can you imagine doing this in a relational database where you're inserting a lot? Exactly. It's not viable, not even by a long shot. But because the structure's in Redis, you can do this. You can model your application the way it fits in your head, if it just so happens that your data model is not just rows and columns and relations like a relational database. And you can certainly map a lot of those things into Redis, and I've actually done so. I've using a lot of the ideas that are in the book. I built a Redis object mapper for Python that embeds a lot of the concepts of a relational database, minus the relations, but there are still minimal relations that you can perform and actually perform a sort of join between these things.
I confess I had an expectation in asking you the last question that what I was going to get back was it's an in-memory server, so low latency is the main thing, where you have some kind of state that needs to be shared in a distributed system which is largely stateless. That's only possible with low latency. Is the assumption of low latency implied by your response?
No. The additional features that Redis is very fast and that generally has low latency because everything's in memory and you're not pulling data from disk. Most people go to Redis because it's fast. And we get questions on the Redis mailing list all the time asking, hey, I heard that Redis was this really, really fast thing. How do I use it? How would I model this thing? And I understand that people are coming at it because everybody wants things to be faster. And it certainly is fast, and that's one of the first things that got me to it. But after you've been using it for a little bit, then you realize, wait a second, the speed brings me in, but what keeps me here is that I can build rich data models. It reduces the constraints in your modeling in some ways by just giving you different opportunities. And certainly the speed is terribly important. I think that if Redis was 1% of its current speed, I don't really think that anybody would use it because it'd be practically too slow. But as it is, it's fast enough, and you get it's faster than a lot of other software equivalents, and it offers the rich data model that helps you in actually getting your application built.
I know I could go on and on this direction, but I want to switch to discussion of persistence. Redis offers two different persistence models, BGSave and AOF. Could you tell us about what those do and how they differ?
Sure. So BGSave is actually the command that you execute to initiate a background snapshot. Snapshots are point-in-time snapshots of your data. What happens during a snapshot is Redis forks itself using the standard POSIX fork call, which creates a copy of the process, and then the child copy will then examine all the data in Redis and dump it to disk into a snapshot file with the extension RDB. And after that is done, then it renames the file, overwriting the old snapshot, and then returns back to the parent process, which then now knows that all the data has been saved, and so records information about that so that you know when the last time it was saved. You can make this operation automatic with the save configuration, and there you go. So the nice thing about that particular form of persistence is that if you need to have your data at one point in time, you can get it. The snapshotting mechanism is also used to initiate slaving replication. I'm probably getting ahead of myself. You'll probably ask about that soon. On the other hand, the AOF, or append-only file, how that operates is any time that there's a write operation to Redis, Redis will write that write command to disk into this append-only file. It behaves very much like a traditional database's commit log or write-ahead log, or sometimes called intent logs. It behaves very much like that. The only real thing that you need to be concerned about there when using it is how often you want to sync the data to disk. How often you want to make sure that data definitely, absolutely got to disk. There are three options for that. One is don't worry about syncing the data. Another is sync the data to disk once every second at least. And the third is sync for every write command. And the latter slows down your machine. The 1 second typically gets you more or less unchanged Redis behavior depending on the volume of your writes and how large the write volume is. Say for example your write commands are taking 150 megs a second. Well, you're going to have a disk that does 150 megs a second write. Depending on the situation, I will sometimes use AOFs, sometimes use snapshots. I will sometimes even use both, depending on how anal retentive I want to be with my data.
Even with both, Redis with persistence is not as durable as an ACID database, which promises that it will not tell you your transaction has been committed until those bytes have been written out to a spinning drive. So this is better than losing an entire server with gigabytes of data. So what problem does the persistence solve within the realm of an application as a whole, and when might you use it versus just running it without persistence and saying if I lose it, I start from scratch?
Well, so like any other database server, say you've got a Postgres server, okay, just a single Postgres server hanging out on a machine. As you use it, data gets written to disk, and let's imagine that you lose the machine. Literally the machine dies, the disk dies, you lost the data on disk. Well, now you've just lost all of your data. You needed to back up. Redis doesn't solve the problem of backups. Redis solves the problem of, here's a server, we persist data on disk. As long as your failure isn't catastrophic, you can get a pretty good amount of data back. That is, if you're using your append-only file, notice that when I said append-only, you can sync every second at least. In practice, I've seen servers actually sync to disk dozens, hundreds of times a second, sometimes with very fast SSDs. So while it is not guaranteed, like say a relational database, that the data is on disk for these, ACID consistent databases, it does pretty well in practice. So far, people who've had a machine lose power, during many writes, they come back and they've got their append-only file, and their question is, hey, I've got an AOF. When I try to load it, it fails, saying that some of the data has been corrupted. How do I fix it? And then somebody says, run this command with these options, and it strips off the corrupted data at the tail end of the file, and they recover, and almost invariably they say, I think I lost 3 writes, which, wow. Hey, we were doing 10,000 writes a second, lost 3, from a data, from power outage. That's not bad, okay? Not perfect, but not bad.
Sounds like a very impressive trade-off between durability and performance?
It certainly helps. Now, it's also the case that if you have, say, a solid-state drive, you can do better. If you let it, sync with every write, then of course you can guarantee that you get all of your data back. But then even then you may have to worry more about the solid-state drive's ability to actually write data in the case of a power outage. You've got to worry about all these other things. In a lot of ways, when you're, to pull ourselves back a little bit, to worry about the particular details of a byte on disk is important. When you really start worrying about them, then you start to understand that most computers out there that already exist are not terribly reliable data storage devices. And even solid-state drives, there was an article a couple months ago where it was shown that Intel's solid-state drives, when they say that they're safe for power outages, really are the only drives that are safe for power outages, and that other solid-state drives from other manufacturers, even though they say you can pull the plug and all the data that was claimed to be written is written, they lie, and they get data corruption, and sometimes irreversible cell damage on the drives. So whether or not Redis itself actually says it got data to disk versus what you read, using, say a single spinning disk in real hardware sitting on your desk to store data, still not all that terribly reliable to begin with.
I'd like to switch over to talking about Redis from a programmer standpoint. How widespread is the support for different programming languages on the client?
So last time I checked, there were more than 30 languages covered in terms of clients. A quick check. Let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I lied. 29, unless I miscounted my quick pass. There are also, collect almost countless higher-level tools, and most of the programming languages covered, that have clients, have a few clients. I mean, heck, Go's got 8 or more clients for Redis, which is kind of crazy, and Java's got a similar number. The language support is pretty expansive. I mean, it covers more or less all the major programming languages and a lot of what I would consider to be minor programming languages as well. It also, the protocol itself is also not that bad to implement. While the protocol has changed since version 1 to the now 2.8 and soon to be 3.0, it's not difficult to implement the protocol if you've done it before. If you've developed protocol communication before, it's not difficult. As a new project, I may take a little bit longer, but it's not bad.
And are people typically doing anything like an ORM mapper or some kind of a bridge from the data structures in their programming language to Redis data structures, or do the uses that they use it for not necessarily require that?
Really, it depends on the use. There are a lot of people that are using Redis without any sort of mapper of one kind or another, an object mapper at all. They're using it for leaderboards in video games. They're using it for cookie storage. They're using it for all sorts of things that don't necessarily require that kind of access. Most of my usage up until relatively recently was, just data structures in the raw. More recently, after having a need for actually modeling data, like a traditional object relational mapper or relational database, I looked around for existing object mappers for Redis, and I didn't particularly like the features or functionality provided or the way the API worked, and so I ended up building my own. I don't, to be honest, I don't use mine very often. I will use it here and there for relatively small things, sometimes when I'm building a new proof of concept application, I will use it as the only data store, and I will just use my Redis object mapper for Python, and that will typically get me started in 5 minutes. I don't need to worry about database configuration. I don't need to worry about setting up a new user and all that other stuff on my database. I don't need to worry about, okay, now how do I initialize this thing here? It's just a connection string, and I just don't worry about it. It behaves more or less as I expect because I wrote it. But different object Redis mappers will have significantly different features. Some are strictly just, okay, so you've got a hash in Redis, you want to be able to pull data out and put data in, and that's the level of abstraction. Some improve or offer an abstraction for set manipulation. Others don't. What features you get will vary based on programming language and library, of course, but there are a lot of them. I know at least 4 in Python. I've seen 3 in Ruby. I know there are a few in Java, although the people that I've talked to that use Java are sad that it doesn't have all the features that some other libraries have. So whether or not an object mapper exists or is useful will vary greatly.
I'd like to move on and talk about some of the infrastructure and performance issues. How much memory are people able to allocate to a single Redis instance, and what's typical?
If you're using a 32-bit version of Redis, then you get 2 or 3 gigs depending on your operating system. With 64-bit Redis, you can, which is fairly typical nowadays, you can have as much memory in Redis as you have memory on your machine. I've personally used Redis servers with, back in the day when Amazon's largest instance was 74 gigs of memory. I used those, and I was using 40 or 50 gigs of those at one time. How big is viable will vary based on the types of operations you're performing. In particular, if you have very expensive operations that you're performing, say you were intersecting large sets or performing some of these somewhat expensive set or sorted set operations, maybe a single large server doesn't make as much sense because then you have a lot of clients trying to manipulate all of the same data. And you could become CPU constrained because, again, single threaded. But if most of what you are doing is using it as a data storage platform, the large Redis instance I was talking about earlier, that was for a Twitter analytics platform. And though it was performing a large amounts of reads and writes, none of the operations were expensive. And sure, we sustained fairly consistent, 50 to 60,000 read and write operations a second. None of them were expensive. So it would typically run in the 20 to 30% of one CPU, which was great for us. We could do high I/O. We could store a huge amount of data, and it was fine. I'm positive that nothing else at the time could do it.
If I'm running a Redis server, then from what I understand, I would look at, if I wanted to add more memory, I would watch the CPU and the number of operations and look at what point does the CPU start to become the bottleneck, because being single-threaded, I can't add more CPUs to it.
Certainly. That is definitely the case. You would check your operations, see if it would perform. That said, it's not impossible and not unreasonable, actually, to run multiple Redis servers on a single physical machine, or virtual machine, as the case may be. The memory overhead of Redis itself is only a couple megs, so there's actually groups of people who advocate for running several Redis servers, Redis server processes on a single server itself, running on different listening ports and pre-sharding data, so that if later, when you need to really grow them up further, say you run 4 Redis processes on a single machine, if you ever need to grow, then you can use some replication techniques to actually migrate the data to another server, and say reduce your number of Redis processes from 4 to 2, and then from 2 to 1 as necessary. There are some that even suggest going way farther if you know you're going to need a lot of data, and starting with 64 Redis servers on each machine, and going from there. I'm not sure I would go that far. And I've personally had pretty good luck with running a single server and then partitioning data later. But it's all about where you want to do your work. Do you want to do it up front, or do you want to do it later?
If I'm looking at an application with a large number of keys, what is the algorithmic complexity of Redis key lookup, and how does it scale to huge numbers of keys?
So it's order 1. That is, Redis's main table for looking up keys is a hash table. So you need to calculate your hash, you need to look up in the hash table, and because Redis actually uses what is called buckets and linked list chains, depending on how full the main hash table is, I will have to look through a few items. Redis does automatically resize its own hash tables, so it is possible that you will need to check 2 entries, the current hash table or the old hash table, and then the other one. But still, it's very fast. The actual major performance issues with Redis that stop it from going from, say, 100 or 200,000 operations per second on a reasonable sized machine to say millions, tens of millions, the same thing that stops just about every other system from doing it, which is network I/O. So generally speaking, Redis is usually constrained by network I/O more than main hash table lookup by a couple orders of magnitude.
You've talked about earlier the idea of a master-slave, and just a moment ago about running multiple instances of Redis on the same box. The number of options for scaling out Redis, could you tell us what they all are?
Certainly. The simplest way to scale Redis is to put Redis on a bigger machine with more memory. And that's the typical thing that most people do until they can't reasonably afford such a large machine, or they can't get a larger machine. The second is, if you have not heavy writes, say moderate writes, but you have a lot of reads, another common tactic is to add read slaves. So Redis has this concept of master-slave replication, and you can attach ostensibly as many slaves as you want, although beyond a few, what you can end up with is outgoing bandwidth limitations from your master. Say, for example, if you've got a master and 50 slaves, every write that hits the Redis master will then be replicated out 50 times the slaves. That's not really viable in practice, but because Redis slaves also can slave themselves, you can set up a tree type structure to do that. There's actually a user that asked about a similar scenario in the last couple of weeks on the Redis mailing list. In any case, so you can slave for reads. If you need to handle a higher volume of writes than what Redis could normally handle, or more than would be reasonably replicated out, you can shard your data. That is, you can run multiple Redis servers, and you can use, say, key sharding or some sort of data sharding to partition your keys from a single Redis server across multiple Redis servers. And there's actually a tool called TWEM proxy, TWEM proxy. It's a server that Twitter had actually developed to proxy sharded Redis database calls as well as memcached calls. It supports both. And so if you want your clients to not have to worry about sharded data, you can instead have a collection of proxies that handle the sharding and all the connection management, and then you can just hit those proxies.
And if I'm starting to shard the data, then does that shift the balance as far as what operations can no longer be done on the server? Some of the set intersects and complex multi-valued operations across different shards?
Yes. Unfortunately, when you partition your data like that, you are no longer able to perform multi-key commands that involve keys from different shards, or at least data that's living on different Redis servers. Redis doesn't really have a concept of data migration, and when you are manually sharding like this, Redis won't even know that it has a portion of the data and not all data. There is a service, there is another way of scaling out called Redis Cluster, which is currently in beta. It's currently the priority for Salvatore, the author of Redis, which does offer a bit more automated scaling out and automatic sharding and replication and a few other features. But it also is limited to these multi-key operations where all the keys live on the same server, potentially, but must be in the same, or I believe, at least right now, are required to be in the same data shard. Although it does let you specify how you want to shard your data. So you can force data that should live on the same machine to live on the same machine. Say, for example, you have user data, so you've got your cookie for that user, their visiting history on your web page, and a few other associated pieces of information. You can tell Redis and your sharding mechanism all of this data should be on the same machine, so it will all be on the same machine.
In relation to the master-slave, you mentioned earlier that it uses the same forking process as bgsave. How does that impact the fraction of the machine's memory that can be allocated to Redis? And where I'm going with this is, do you need to be cognizant of how the fork is going to require a chunk of memory?
Certainly. That is definitely a concern. The typical super anal retentive developer and an architect will say, Redis must only use half of the memory on a machine. Just in case we've got huge volumes of writes when we are snapshotting in preparation for replication, or as part of the typical saving process. Because of this fork, if we've got enough write operations, we could actually double the amount of memory that Redis is using. Potentially even more if the amount of data in Redis is growing fast. What Redis does is it actually informs you in the log file of how much memory was used by the child process, additional memory. And so depending on your operation, if you pay attention to your logs, you can discover how much memory is actually being used by that operation. So you can actually appropriately size the amount of memory that you're storing in Redis compared with how much memory is available on the machine and how much memory that a fresh snapshot for slaving or for just snapshotting and keeping your data. So you can properly size all of those things. It's not perfect, but it can give you a pretty good idea.
I've looked a little bit at Redis Cluster and Redis Sentinel, which is a different project that has some of the same goals. I've been following some of the discussion on the Redis mailing list, and this is how it appears to me, is Redis is a brilliant solution to the things it does well, and a lot of that is based on the fact that it's single-threaded and runs in a single address space. And when you try to scale it out, it becomes a distributed system, and then you're moving more in the direction of a Dynamo-type store, which is a different animal and requires a whole different thought process in order to do what those data stores do well. Now, am I being unfair here, or how would you respond to that?
I think you might be being just a smidge unfair. You know, there are a lot of operations that Dynamo and, generally speaking, you know, a big table-like data server offers. You know, one of the most important being you can put a huge amount of data in it. But how those systems work primarily is put your data somewhere, optionally with indexes, and if you want to perform a query, basically perform your query against every machine with data that you care about. And so in a lot of ways, it kind of sort of acts like a MapReduce operation across all of your servers. And in fact, there are several databases that's all they do. They just store data somewhere, and then if you want to query the data, you perform a MapReduce. Redis, on the other hand, is not necessarily meant to store terabytes of data. You know, it's not necessarily meant to be your archival data storage solution for the next 20 years. It's not meant to perform cohort analysis on 30 billion video views over the last 2 weeks. That's not what it's for. It's for storing, you know, in some sense, data that you need to have, number one, fast access to, number two, access in certain structural ways that are fast, okay? You know, because typically you look data up via keys or via some index that you've manually built in Redis, and that's it. You're typically not saying, you know, count the number of items with this certain feature and group them by this. It's a more typical operation that you would perform on a Dynamo or a big table. And so the data you're storing is different, the data access characteristics is radically different, the data storage, you know, the types of data that you're storing is radically different. Certainly, you know, to get back to your real question, does it get more complicated? Absolutely. You know, it's no longer the simple, oh, I can intersect anything, or oh, I can sort anything and I can access any type of data anywhere. It stops being that. But a lot of those same constraints exist on relational databases where you also have to shard.
Sure, definitely. In fact, I'm thinking of a clustering solution for MySQL where you can't do joins anymore.
Exactly. And there's a similar package for Postgres where maybe this was a decade ago where this is the case, where you know you had to perform your queries against each of your sharded servers, and then you had to merge the results yourself. That was fun.
Exactly. You talk a little bit about the open source project. How many committers are there? How active is the community? What resources are out there?
So Redis itself, you know, it has a primary author, and that is Salvatore Sanfilippo, the inventor and original author. It was his idea. He developed almost all of it. Now, it certainly is the case that there are more contributors now. As time goes on, you know, of course, more and more people get patches in. I personally only have a single patch in Redis, even though I've been using it for so long. And it was for an early feature that allowed you to perform Z interstore and Z union store on sets as well, where you could pass in a set. You know, a quick check of the statistics from the Redis repository says that Salvatore has got by far, you know, a factor of 10 more total lines committed than the number 2, Peter Nordhaus, who, at least in the past, was at least partly employed by VMware, now Pivotal Labs, as Salvatore's number 2. But it would seem that he has ramped off the project, and some other people have started to become more active. But primarily it's Salvatore. So as a almost one-man piece of software, it's pretty amazing what he's accomplished.
There's also a mailing list which you are very active on.
So the Redis DB community mailing list. I originally joined it shortly after starting to use Redis in order to ask some questions and to, even offer some feature requests and a couple patches. And then, people started asking questions, and I started answering them, and have kept answering them. And people keep having interesting questions, and I keep learning more about Redis, and so I keep answering the questions because they're fun. I've done this before in some other mailing lists in the past, but it just so happens that that at least for now I'm hanging out on the Redis mailing list, and actually that's how I ended up writing the book. A publisher Manning saw how prolific I was in the mailing list and said, hey, this guy probably knows what he's doing. So I got a call, and there was some negotiation, and I wrote the book more or less based on the problems that people were bringing up in Redis, in the Redis mailing list. Common problems, common solutions, common ways of looking at very typical problems.
In addition to your book, was there anywhere else that you would like to direct listeners who want to follow more about your work? I should say the book and the mailing list, because you're very active on the mailing list as well.
Other than that, periodically I post blog updates, and sometimes I talk about Redis, sometimes I talk about Python, sometimes I talk about other things. Recently I even posted about my experiences with Soylent, which is a nutritional product, a meal replacement powder that I had helped kickstart last spring, or I guess early last summer more likely, or crowdfunded it. I'm sorry, it was not on Kickstarter itself. I typically post about a variety of things, mostly being Redis or Python. Sometimes I talk about general tech, sometimes I talk about, periodically I will talk about politics, but for most people, or at least most engineers in the Bay Area, or most engineers generally, I'm not going to be terribly offensive.
We'll definitely link to your book and your blog in the show notes. Josiah Carlson, thank you very much for speaking to Software Engineering Radio.
It's been my pleasure, Robert. Anytime you want to talk again, I'm available.
Thanks for listening to Software Engineering Radio. We want to know what you think. Go to iTunes and write a review of the show, stating your opinions. It would help us improve the show. Thanks.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To support us, you can advertise SE Radio by clicking the Dig, Reddit, Delicious, or Slashdot buttons on the site, or by talking about us on Facebook, Twitter, or your own blog. If you have feedback specific to an episode, please use the commenting feature on the site so that other listeners can respond to your comments as well. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Please see the website for details. Thanks again for your support.